Let's discuss the consequences of our calculation of the coefficient of viscosity. So we can recall that the mean free path, that is the mean distance between successive collisions, we have estimated to be 1 over square root 2 number density times scattering cross section sigma. So if we insert this into our equation for the coefficient of viscosity eta, which we found to be 1/3 and v bar, the mean speed per molecule, multiplied by m times the mean free path. So this is going to be 1/3 and v bar m 1 over square root 2 and sigma. So you can see that these n's will cancel here, and we will have also for v bar we need an estimation, so we can estimate the value of v bar by considering the equipartition theorem. We have 1 over 2 mv square is equal to 1 over 2 m vx square plus vy square plus vz square. And remember, each independent quadratic degree of freedom will give us a 1 over 2 kT contribution to the thermal energy. So this gives us 3 over 2 kT, and therefore we find that v square bar is equal to 3 kT over m. So now if we have the following approximation, v square bar, the mean value of the square of the speed, is approximated to be mean speed square, then we can see that this approximation will give us for the mean speed square root 3 kT over m. Now this actually again is not a very rigorous calculation, so if you remember, we did this properly using Maxwell's speed distribution before, and we found that the most probable speed is square root 2 kT over m. The mean speed was square root 8 kT over m pi, and RMS was square root 3 kT over m. And you can see here that basically we're neglecting the difference between VRMS and V bar in this calculation as an approximation. So it's approximately square root 3 kT over m. So substituting these values for eta here, we obtain for the coefficient of viscosity 1 over 3 square root 2. For V bar, I substitute square root 3 kT over m, and then we have a factor of m divided by sigma here. So this is going to give us for eta, it's going to be 3 square times 2, so this is going to be 1 over square root 3 square times 2, and then I have a square root 3 here, and here I have square root m square kT over square root m and 1 over sigma. So this is going to give us for eta 1 over square root 6, because this square root 3 will get rid of this square, and then we have the m's cancelling, square root m's cancel, and we obtain 1 over square root 6 square root mkt thermal energy divided by sigma. So using this estimation for the mean speed per molecule and the mean free path, we obtain 1 over square root 6 square root mkt over sigma. Now I want to concentrate on dependence on n, the number density, and the mean pressure. How does the mean pressure and how does the density of molecules, number density, affect the coefficient of viscosity? Well, this formula basically tells us that eta is equal to, or estimated to be, 1 over square root 6 square root mkt over sigma. You see no n here, so this suggests basically eta is not a function of n. Eta is independent of n, the number density, which is capital N, number of molecules divided by the volume V. And also, since we have for an ideal gas P bar V is equal to capital N kT, number of molecules times Boltzmann constant times temperature. So since P bar is equal to n lowercase n, the number density, and kT, for a fixed temperature, we also have no dependence on the mean pressure. So basically, eta is not a function of n or P bar for temperature fixed. So this is basically our conclusion based on this analysis. Now we can justify this by trying to double, for example, the value of n. So let's try a justification here. So let's say that n is doubled. So if the number density is doubled, that means L, which is 1 over square root 2, and sigma will be halved. So the mean free path will decrease. So we're going to have the rate of momentum transfer that's going to be unchanged. So we have explicitly here for eta, the coefficient of viscosity, 1 over 3, n has become 2n, V bar m, L is divided by 2, so you will have these two canceling each other and the same value for the coefficient of viscosity. So this basically relies on the following assumption. First, we have the mean free path much greater than the diameter of the molecules, and the diameter of the molecules is proportional to total scattering cross-section to the power 1/2. So if you remember, if d is equal to 2a, total scattering cross-section becomes 4 pi a square, or pi 2 d square. No. So d is equal to 2a, so it's going to be pi d squared. Now the second assumption here is that we have the mean free path is much less than the dimensions of the container. So L is dimension of the container, the length of the container. And you can see that this assumption implies that molecules collide predominantly with other molecules. Rather than the container walls. So there is one problem with this if we have a vacuum. In vacuum, we have the mean free path approaching the dimension of the container. So there is nothing else to collide with. So basically, we would have a molecule that would collide with the walls of the container, but nothing else. And the number density is decreasing. So in vacuum, the number density is going to 0. And we find that eta, which is 1 over 3 and V bar ml, because L is replaced by 1 over 3 and V bar m capital L, as n decreases, eta should decrease as well. So as n goes to 0, eta goes to 0. So it does have a dependence on, it becomes a function of the number density in this limit. So in the limit of having a good vacuum condition. Now we can take a look at the temperature dependence. So for the temperature dependence, we can see explicitly eta is proportional to T to the 1/2 divided by sigma. Why? Because we found that it is 1 over square root 6 square root mkt divided by sigma. So the temperature dependence will not come from mass or the Boltzmann constant. It can only come from the explicit dependence on temperature divided by sigma. So actually, this suggests that eta increases with temperature as T to the power 1/2. However, sigma, the total scattering cross section, decreases with increasing temperature, which is not explicitly taken into account in this theory. So because we have treated the molecules as hard spheres, but actually they're not. There's a bond between atoms that forms these molecules, and so sigma decreases with increasing temperature. So we find that in reality the coefficient of viscosity increases with temperature more rapidly than T to 1/2. It's more like T to 0.7 dependence for gases. Now, why did I say gases? We were talking about fluids. Actually, there is a difference in the behavior for gases and liquids. So in liquids, actually the mechanism with which we have the transfer of momentum is different. So in liquids we find that as opposed to gases, the coefficient of viscosity actually decreases rapidly with increasing temperature. And the reason behind this is basically the fact that the way these liquid molecules interact is through direct forces. So liquid molecules interact with direct forces, not just transfer of molecules across the plane. So this is not something we have considered here. We're only considering the dilute gas limit, where we have only the transfer of molecules contributing to momentum transfer. But here actually we have a different mechanism, the mechanism of direct forces, interaction through direct forces. So basically our theory is not valid anymore. So we find that instead of increasing with temperature as T to the 0.7 in gases, the coefficient of viscosity tends to decrease rapidly with increasing temperature in liquids. Now, finally, let's calculate a typical coefficient of viscosity for a gas, for a dilute gas. So you can see, for example, if we consider the nitrogen most abundant gas in our atmosphere, the mass of one molecule is 28 grams divided by Avogadro's number, 6.02 10 to 23. This gives us 4.7 10 to minus 23 grams. And let's assume the temperature is 300 Kelvin. So for mv bar, we can estimate this to be square root 3 mkt, which is 2.4 times 10 to minus 18 grams per centimeter. We can estimate the diameter of a molecule to be 2 times 10 to minus 8 centimeters. The total scattering cross-section we can estimate to be 1.2 times 10 to minus 15 centimeters squared. Remember, this is 4 pi a square, or pi 2d square. Pi d square, because d is equal to 2a. So we can basically see that the coefficient of viscosity is 1 over 3 square root 2 mv bar divided by the total scattering cross section, and this gives us 5 times 10 to minus 4 grams per centimeter second. So in units of poise, this is 5 times 10 to minus 4, 10 to minus 3 kilograms, 10 to minus 2 meters per second, a meter second. So this gives us 5 times 10 to minus 5 poise for the typical value of coefficient of viscosity for a dilute gas, so in this case the nitrogen gas. So let's summarize what we said here. We have found out in our previous discussion that the coefficient of viscosity is 1 over 3 mv bar ml, and number density v bar is the mean speed per molecule, m is mass of one molecule, and L is the mean free path. And since the mean free path we have estimated to be 1 over square root 2 and sigma, where sigma is the total scattering cross section, By substituting this into our coefficient of viscosity formula, and we can estimate V bar by saying V bar is very close to VRMS, we find that eta is 1 over square root 6 square root nkt over sigma. So this explicitly suggests that there is no dependence on n, and because PV is equal to nkt, P bar is equal to number density times thermal energy kT, we find that for a fixed temperature there is no dependence on pressure, there is no dependence on number density for the coefficient of viscosity. And indeed, if we double the number density, the mean free path will be halved, so it's going to be cancelling. Well, this relies on the assumption that the mean free path is much greater than the diameter of the molecules, so the molecules can be treated as points, and this mean free path is much less than the length of the container, so there is no collision with the walls of the container that's being considered here. All collisions occur with the predominantly occur with the other molecules. But in vacuum, this mean free path will approach the length of the container and will approach zero, and we will find that the coefficient of viscosity will approach zero. So in vacuum, the coefficient of viscosity will be very low. So there will be a dependence on N and P, the pressure in the limit of very low pressure or very low number density. The temperature dependence comes from the explicit dependence T to 1/2, which comes from V bar, the mean speed of the molecules, divided by sigma, which is the total scattering cross-section. Since we're treating these molecules as hard spheres, we have assumed no temperature dependence of sigma, but actually they include bonds and they have a temperature dependence, so it's more like T to 0.7 dependence for gases. In liquids the behavior is different because we have momentum transfer not just by the transfer of molecules, also through interaction with direct forces which dominates the process. So in liquids actually the coefficient of viscosity decreases with increasing temperature. Then we have estimated the typical coefficient of viscosity for a nitrogen gas. We can calculate its mass by molecular mass divided by Avogadro's number. We can again estimate V bar from square root 3 kT over m, so mV bar factor we can estimate. We can estimate the radius to be 10 to minus 8 centimeters or 1 angstrom, which is 2 Bohr radii. This gives us basically, by substituting these values into the coefficient of viscosity, 5 times 10 to minus 5 poise for a typical coefficient of viscosity of a dilute gas.